Okay, class. So this is another topics in machine design. This is again under the fundamentals. Okay. So by this time, so I will give you the discussion on torsion. Okay. So what is a torsion? So torsion, so an action of twisting or the state of being twisted, so especially of one end of an object relative to the other. So this is class the illustration of a shaft under torsion. So we have here angle theta, or this is the angular deflection created if it is subjected to a torsional load. Okay, so we have here the length of the shafting and the diameter. Okay, so the basic formula for torsion is of course 16t over pi d cube. Okay, so of course this formula is derived from the basic equation for torsion, which is Tc over J, or torque multiplied by the distance from neutral axis to the outermost fiber divided by the polar moment of inertia. Okay, so J. Okay, so substituting the values, so we derive the equation tau is equals to 16t over pi d cube. So therefore the stress of the material is in terms only of the torsion and the diameter. So especially if power of the shaft or power of the driver shaft is given, so the power, so we can easily determine torque from the formula. Power is 2 pi Tn over 60 or Tn over 63025. Okay, so for hollow shaft, so tau is equals to 16 Td over pi d to the fourth minus d to the fourth. So this is for hollow. Okay, so this is also derived from the original equation Tc over J. Okay, so where d is the outside diameter of the shaft, d is inside diameter of the shaft, and T is the torque transmitted. Okay, so next is the torsional deformation. So this is also the basic equation is TL over JG. Okay, so torque multiplied by the length of the materials, and then the polar moment of inertia, and the modulus of rigidity. Okay, so this is the basic. Take note, class, that the unit for the angular deflection here is in radian. Okay, so we have here an example for torsion problem. Okay, so determine the diameter of a solid shaft used for a 500 horsepower, 250 revolution per minute application if the allowable torsional deflection is 1 degree in a length of 20 diameters, and the allowable stress is 10,000 psi. Use a modulus of rigidity of 13 times 10 raised to 6 psi. Okay, so we have here the given 500, the torsional deflection of 1 degree in a length of 20 diameters, G is 13 times 10 raised to 6 psi, and L is 20 times the diameter. Okay, so we have here now the solution. Torque is power equals to power multiplied by 63025 over N. So take note, class, that the given is in English. Okay, so that's why we use that formula. So substituting values, 500 multiplied by 63025 divided by 250, or the torque now is 126,050 Nm. Okay, so getting now the torsional deflection, TL over JG. Okay, substituting the torsional deflection, which is 1 degree, and then changing it to radian, is equals to the torque, which is 126 0.50 multiplied by the length of 20 times the diameter, and then multiplied by 32. So that is from the formula pi d to the 4th over 32. So, and getting J for the polar moment of inertia, and then over pi of this to the 4th multiplied by 13 times 10 raised to 6, which is the modulus of rigidity of the materials. And then getting class the diameter, so that is 4.84 inches. So, getting now the commercial size of the shaft, that is 4 and 7/8 inches. Okay? So, I think it is clear to everybody. Okay? So, another example class we have here, a hollow nickel steel shaft whose outside diameter is twice the inside diameter is to transmit 1,492 kilowatt at 2,200 RPM. The shaft is subjected essentially to torsion, okay? Assuming an allowable shear stress of 224 megapascals, determine the size of the hollow shaft required, okay? So, given D is equals to 2D, B is 1.92 kilowatts, N is 220, and the stress is 224 megapascal. So, that is the allowable shearing stress. Okay, solution now. From the equation for hollow shaft, the maximum shearing stress is equals to 16 TD over pi d to the 4th minus d to the 4th. Okay? So, from the equation, so take note that the given here is in SI unit. So, take note that the power here, so we have here the denominator of 9.54 times 10 raised to 6. Anyway, this is just only a conversion. Okay? So, do not be misinterpreted by this constant here at the denominator rather. Okay? So, but anyway, the power is defined in terms of power equals to 2 pi Tn over 60. Okay? So, just use that equation. And then, getting now the torque in terms of Newton meter. So, that is 4,759,581.82 Newton meter. Okay? So, getting now the diameter, that is equivalent to 116.24 millimeter. Okay? So, another example class we have here. Maybe this is the last example in this presentation. So, a 3-inch or inches solid shaft is replaced by a 3 inches outside diameter and then 1.5 inches inside diameter hollow shaft. So, determine the percentage of reduction in torsional strength. Okay, so actually class, here, of course, the shaft which is most stressed, of course, is the hollow shaft. So, that's why, if we compute the stress, so we will notice that the value obtained from the hollow shaft is greater as compared to the solid shaft. Okay? So, getting now the percentage reduction of the strength. So, percent reduction is equals to stress for hollow shaft minus the stress for solid over stress for hollow. So, we multiply this by 100%, okay? So, substituting now the formula. So, for the hollow shaft, that is 16 TD over pi d to the 4th minus d to the 4th. Minus for solid, 60 over pi d cube over the solid, okay, which is 16 TD over pi d to the 4th minus d to the 4th. So, dividing now, 16 TD over pi d to the 4th by 16 TD over pi d to the 4th is equals to 1. So, and then, 16 TD over pi d cube divided by 16 TD over pi d to the 4th minus d to the 4th. Okay? So that is now equal to, percent reduction equals to 1 minus, eliminating pi and t. So that is the diameter of the hollow shaft to the 4th minus the inside diameter of the hollow shaft to the 4th divided by the diameter of the solid shaft raised to 4. Okay? So, substituting values now, class. So that is percent reduction is equals to 1 minus 3 raised to 4 minus 1.5 raised to 4 over 3 raised to 4. So that is now 1 minus 0.9375. Therefore, the percent reduction now is 0.625. So multiplying it by 100%, the total percent reduction and the strength of the hollow shaft is 6.25%. Okay? So, that is now the answer. Okay? Thank you very much, class. So, that ends my presentation. Okay?